Okay, back on the Aims inverter, the 5000 watt 48 volt DC input inverter. So I went ahead and ordered 32 of the driver FETs and 8 of the output FETs. Now, as you can see, some of the drivers are missing and some of the outputs are missing because I've already placed 4 of the driver FETs in these 2 positions. And I went ahead and replaced all 4 of the output FETs right here. So let's go ahead and power this thing on with only these 2 stages operating and the outputs. Now this voltmeter is measuring AC voltage on the output right here. This voltmeter is measuring the DC bus voltage across these 4 capacitors that drive these 4 FETs. So let's power this on. I've only got a 2 amp power supply connected, so I'm going to have to pump it a couple times because it wants to go into current overload. Oh, it fired up the first time. Look at that. So I've got 124.4 volts AC output right now, and I've got a DC bus of 137.2 and slightly climbing. Now if I go to frequency right here, I've got 60.8 hertz of AC output. Now remember, this is what they call a modified sine wave. I call it a stepped square wave. So let's go ahead and replace the other 12 FETs in this unit, fire it up and make sure everything's good, and then we'll go ahead and do the slave side. This is the master side. This is the side with the microprocessor that generates the frequency for the output FETs to operate on. And then these 2 connectors right here do connect over to the slave side. So let's power this thing down. And I'm going to go ahead and discharge this. It's in the low ohms range, 3000 ohms load impedance right now. And you're just going to go ahead and discharge that back down to 0, so we're safe to work on this thing. Otherwise, the DC bus stays live. So if I go just to volts, you'll see it just floats right there. So I need to go to the low impedance mode of this meter, and it puts a 3000 ohm load across the lead inputs. Okay, so I did this off camera, but I'll do it on camera just to show you guys. Checking the 10 ohm resistors, the gate drive resistors, to make sure none of them are compromised. So very easy to do. You can actually just measure across each resistor and you should get 10 ohms on the meter. But I'm going to cheat. I'm going to go from gate of this FET to the gate of this FET, and I should get 20 ohms. And I do. 20 ohms, and I get 20 ohms. Now we'll go this way, and I'm seeing 24, so now I'm going to measure these resistors. 10 ohms on that one, and I'm seeing 14 on that one. I might want to go ahead and replace that one resistor. It's just slightly compromised, but it is actually working. So 24, 20, 20. So that one resistor is questionable. I might go ahead and get one off a donor board and just go ahead and replace that one just to be safe. But let's measure the other resistors on the other side of the board. 20, 20, and 20, perfect. 20, 20, and 20. I love it. So with the exception of that one gate drive resistor, everything else checks perfectly fine. So I do have a couple of these things that were abandoned. I'm going to go ahead and rob a 10 ohm resistor off of one of them and replace that one resistor just to be safe. Okay, 10.2, I'm happy with that. And off the donor board, I'm going to go ahead and replace that coil that's been burnt, because here is the replacement coil. Looks much, much better. So let's go ahead and change that out as well. So I should have recorded it, and I'm sorry that I did not, but I did test the donor inductor, and it measured 0.09 millihenries. And so we'll test this one. Same resistance, 0.4 ohms, but this one tests 0.02 millihenries. So if you look closely on this thing, you'll see a lot of bare wires, and I think the glue compromised the enamel on the wire. There's probably a shorted turn, because I definitely see some bare wires on this thing, especially right there. That one has been running very cool, which means it has not been dissipating current. So chances are there is a shorted lead. You can actually look up here and see all the corrosion on the wires. So I'm betting that there is a turn-to-turn short on this coil, but I think the new one is going to be just fine. Okay, here we go. Let's fire this thing up and see what happens. I'm betting it's not going to start the first time because it's going to go into overload. I'll have to reset it a few times to charge all these capacitors. Yep. It's trying. I'm going to have to bring it up slowly. There we go, we got it started. So I've got 124.6 volts AC output at 60.85 hertz. And my DC bus is 138.6 volts. It's running very low current at this point, almost non-existent. On the 2 amp scale, I'm drawing probably 100 milliamps because I have no load on this thing whatsoever. But it is working. The master side is repaired, drawing much, much less current because of this coil that's barely warm whatsoever. So that is a very good sign. I'm very happy with this side. So next, the same thing on the other side, 16 FETs and 4 output FETs. Just in case you're curious, there is the voltage on the low impedance mode with 3,000 ohms across it. It did raise the power consumption by about 100 milliamps. So yeah, we're at about 150, 160 milliamps right now. And they were at about 110 milliamps. So it definitely does raise the power consumption slightly because this meter like I said, does have a 3000 ohm input resistance in the low impedance mode, the low Z mode. And that's mainly to reduce ghost voltage on AC circuits, which is why I love this meter. This is the meter I use in my industrial electrician job, my other main job that I have. Okay, on to the slave board. Let's rip 16 FETs off the driver stages and the 4 output FETs off of this unit. And this time I will check all of the 10 ohm resistors with the FETs removed. And we'll go ahead and show you how to check the 10 ohm resistors here. And there's a couple of 1N4148 diodes that you can barely see down here. And a couple of 1N4148 diodes there we need to test as well. So let's get started. Okay, so we'll do the gate to gate check. I want to see 20 ohms. Perfect. Very happy with that side. $22, I might want to change one of those resistors. Yep, 22. Okay, so which one is 12 ohms? 10.2. 12 ohms right there. So I'm going to want to change that one resistor. Other than that, all the rest are perfectly fine. So based on that, probably the driver transistors are okay, but I will go ahead and do a diode check on those as well. All right, 10.1 ohms. Perfectly happy with that. Okay, so these are the driver transistors that drive the driver FETs. 630, 611, I'm good with that. Now we have to reverse polarity, so I'll just go ahead and put it up here for these two. 628, 607, I'm good with that. And I shorted the leads out. 630, 611, I'm okay with that. 628, 608, so no short, so I'm just going to go ahead and check collector emitter on all 4 of them. I just want to make sure we don't have a short. Now we might see resistance depending upon which direction the leads are placed. If I can get here without. So see, I have a capacitor charging there. So as long as I don't see shorts, I'm perfectly happy with that. Let's go and check the other 4 on the other side now. Okay, same rules apply. So we'll go from the center lead. Hopefully you can see it on the camera. 608, 628, then we'll reverse the polarity. 630, 611, I'm good with that. Same thing here. 628, 608, that's actually voltage that I'm reading, 0.607 volts. Then we'll reverse the leads for the opposite transistor, 629 and 610. Once again, shorts, collector emitter. No short. No short. And capacitor charging, perfectly happy with that. As long as it gets up to pass to about 0.6 of a volt or more, I'm good. And 1.15, perfectly happy with those driver transistors. Now we'll go ahead and zip off all 4 of the output FETs on the slave board. Okay, there are the 4 output FETs. And of course that one right there definitely has an S stain on it. I believe the other 3 are okay, but we're going to change all 4 of them just to be safe. But before we do that, we need to test these 10 ohm resistors. There's 4 of them. And we need to test these 1N4148 diodes. 2 are easy to test. 2 are in parallel with the 10 ohm resistors. So we can easily test these 10 ohm resistors. 10.1, perfectly fine. 10.1. Now these will actually test as 10 ohm resistors if they're good. 10.1, perfectly fine. And 10.1. Now to test the diodes. These can be tested in circuit with no modifications necessary. 570 and open. 574 and open. But watch what happens when I try to test these diodes over here. 0.009. That's because there's a 10 ohm resistor in parallel with that diode. So I need to lift one end of that resistor to test the diode. Now I can go ahead and test the diodes. 569, open. And because that one got heated up, it's acting as a thermistor basically. But I'm perfectly happy with that, even though it is warm. And open. And so once again, here's the 10 ohm resistors. 10.1 and 10.1, perfectly fine. So I'm very happy with the gate driver stages. Now we can go ahead and solder those back in place. So next I want to go ahead and check these 4 output FET driver transistors to make sure there's no shorts there. So you can see them right here. So as they are facing right now, we have base, collector, emitter on all 4 of them. So in the diode range, we just want to go base to collector, reverse the leads, and I see a junction, and I see a junction, and I don't have a short. This one should be opposite, and it is 615, 616, no short. Six 16, 617, no short. 561, 587, and no short. I'm perfectly happy with those. So let's go ahead and refill this thing with 16 driver FETs and 4 output FETs. But before we refill this thing with FETs, I need to go ahead and get those damaged fuse holders out of the circuit. So hopefully they'll cooperate. I have them marked in red. I'm just going to fill this with solder and kind of try to push them through on the other side of the board if possible. Then I'll try to vacuum out the hole. Oh, that one went excellent. Okay, so got those out. Remember the carnage that these things suffered. Look at the arcing that these two had. And then this one, the reason I changed it out was because it had a big old weld ball in the side of it. I'm not sure I could ever get a fuse back into here safely. But luckily my donor board had plenty of perfect fuse holders, so I think we're going to be just fine. We'll go ahead and get those resoldered in place, and we should be very good to go. Okay, so I'm on the low impedance mode right here on the voltmeter. I have the unit successfully powered up. The slave and the master is connected together. So let's look at the DC bus voltage. And we have 142 volts. And this is the AC output voltage, 124.3. Let's look at the frequency. I'll put it in AC and then frequency. And we are at 60.84 hertz. So I think this is going to be a successful repair at this point. Both halves run in together. They love each other. No conflicts as far as I can tell. So I'm just going to go ahead and reassemble this half because these FETs are just sitting here nice and cool, no current draw. But anyhow, I'm going to sit here and cook for a little bit. And if everything passes in a couple of hours, I'll throw it back together. And I've actually got 4 batteries that I purchased to be able to put this thing under a good load. They're small lawn and tractor batteries, so we should be able to pull. I'm thinking of plugging in a resistive heater at 1500 watts and see if this thing survives. So I did go ahead and plug a garage light into it. We're drawing right at 2 amps right now. And as far as I can tell, we'll still running nice and cool, but yeah, this is a pretty high powered lamp. So it says 80 watts. You can see the amount of light coming out of it, but that is plugged into the inverter right now. You can see it plugged in right there. And like I said, we're drawing right at 2 amps. So let me fish the leads back out here and we'll take a look at the voltage again. So we're at 123.9, 60.83 hertz, and the DC bus 136.7. Well, like I said, just going to let it sit here and cook. I'm sure these FETs are not doing anything right now on 80 watts on a 5,000 watt inverter. So I'm just going to let it cook for a little bit and we'll get it reassembled and give it the final test. All right, so I have the infrared camera out and I'm taking a look at this. There's the coil that got replaced. And we are running about 125 degrees right now. I'm perfectly happy with that. So this is the master board that is attached to a heatsink right now. And you see some reflections. That's pretty normal with an infrared camera. Anything shiny will actually reflect the heat. So this is the board that is not heat sunk right now. And I'm not sure we're actually reading accurate temperatures because of the reflections. Yeah, I'm going to say that that is not an accurate temperature right now. But just looking over here, those are the switching transistors right there that are warming up. 109 degrees, not too terribly bad. And I really can't see the other ones. They're kind of buried under here. Oh, they're about the same, 104. And there's the output FETs. So they are, if I can get zoomed in on just one, 80 degrees. No problem whatsoever there. Main FETs, perfectly fine. Of course, as I move this, because they are shiny, they're reflecting the heat. Let's take a look at the garage light that's running right here. And yeah, 113. See the aluminum fend heat sinks on it. So that's what's going on. What about the power supply over here that I'm actually running this thing on? You can see it's definitely generating some heat. Back here, the heat sink. Yeah, definitely running some heat. 140 for the main output transistor. Yeah, definitely doing some work. So far, pretty happy with this thing. Like I said, going to let it bake for a little bit. Nothing else really getting too terribly warm on here. Everything's looking pretty doggone good. Pretty happy with the results so far. All right, here we go, the moment of truth. Now, I only have these clipped together in case I got to pull them off quickly. So I'll power this thing on. And I get an LED indicator. So this has been sitting in my garage for literally months. Now it doesn't want to run really. Huh. Well, I have it turned on. It's It's on auto up here. Maybe that's why it was slow to power up. And I do have it connected, like I said. I can pull it in case of emergency. There it is, 1500 watts. I do feel heat coming out. Let's plug the kilowatt into it. Okay, garage light is still connected. All the batteries. I have the emergency disconnect right there. And here is the kilowatt. Let's turn this thing over. It's way too freaking bright. Okay, that's much better. Here's the kilowatt. You can see 11 watts. Let's kick this on to on. And we can see just over 1,000 watts right now. 1,213, 14, 1,540 watts. There, it's coming back down. Okay, I'm going to say success. The garage light is running. This thing is drawing just over 1,000 watts right now. And we got it hooked up to the batteries back here. But I'm going to call this a win. Thank you so much for watching the repair on the Aims PWRINV5048W. I certainly hope you enjoyed the repair on this inverter. Go ahead and leave me a question, a comment, a concern down below, good or bad. I try to respond when I have time. While you're done, hit that subscribe button and like this video. It really does help my channel grow. You can follow me on social media, Facebook, Instagram, Twitter, at NorCal715. You can email me, norcal715videos@gmail.com. That is the best way to contact me. Please be patient. I have a full-time job, and I do these repairs in my spare time. Remember, with your help, we can try to keep these things out of the landfill, out of the recycle bin, and out of the e-waste facility. Everyone, thank you so much for making it to the end of this video. I really do appreciate it. Everyone have a great day. Thank you so much for watching once again. Bye-bye.